Good afternoon. We're delighted to have Alexei Borodin, who's really revolutionized our understanding of integrable probability, give the Birnbaum lecture. Please, Alexei.
Thank you very much for the invitation. It's a great honor for me to give the Birnbaum lecture, and a great pleasure to be here in Seattle and in Microsoft. Somehow it so happened that this is my first real visit. So the title of my talk is on the slide. The branching graphs part, I will explain what they are. And let me first say a couple of words about the term integrable probability. It's not such a common thing. It was coined a few years back, and the idea behind it was to have a term for a bunch of probabilistic models where the analysis of the models heavily relies on algebra. So one first does some algebraic manipulations, derives formulas for whatever, your favorite observable in the model, and then only in the end, when the formulas are ripe, you do something to them, you take some sort of a limit, and then that limit gives meaningful probabilistic information, something you wanted to know from the very beginning. This is not a very traditional, at least in modern setup, a very traditional way of analyzing probabilistic models, but probably historically the first one. So the central limit theorem for the sum of dependent Bernoulli variables was proved and published by De Moivre something like 300 years ago, a little less, and that was certainly an example of integrable probability. He computed the distribution in terms of binomial coefficients and then did Stirling's formula, whatever it was called then, maybe nothing, and that gave the Gaussian distribution. So the advantage of having algebraic structures is that they allow to get very fine control on the asymptotics of the model, something that's usually not achievable by more generic methods. The disadvantage, of course, is that they only apply to very peculiar models, and the models are totally not generic. You twist a little thing in the model, and the whole algebraic structure just evaporates. But still, the same way as the Moivre central limit theorem predicted the limit law for a much broader class, the integrable models do predict things for some universality classes, even though the universality classes may be conjectural, not completely clear what they are, but they tell you something about a broader class of models. All right. So in what happened through the last maybe 20 years or so was that people accumulated a fairly large number of such integrable models. And chances are, if you went to probabilistic conferences, you've heard talks about them. Think about TASEP or tiling models or plane partitions with some distribution on them or things like that. In fact, as I'll try to argue, the Poisson-Dirichlet processes that we've heard about in the previous talk should also be placed into the integrable probability realm somehow. Now, it may get confusing, and it does get confusing. How should one think about this bunch of examples? Is it really totally chaotic? And so what I wanted to do is try to tell you how I group these examples in my head. What is the way for me to structure them and to think about them in some subclasses, some categories. And that also, I think, is helpful because it shows some underlying structures that are common for different models, even though the models themselves don't seem to be related. That structure that I will talk about, some sort of an overarching structure, has a name. So this is Gibbs measures on branching graphs. This is a fairly old topic, actually. It was pioneered by Kerov and Vershik in early 1980s. But I don't think it is that widely known, and so this is my way of trying to say that it is actually useful to keep in mind for various things. So branching graphs, what are branching graphs? They will show up in maybe 15 minutes or so, but these are examples of branching graphs. So this is the Pascal triangle, and this is the so-called Young graph, where the pictures are Young diagrams or staircase-like objects built from one by one boxes, and then the edges are adding a single box to them. All right, I don't want to be completely general and sort of give a high-level nebulous talk, so I want to have one concrete example in mind that gives a concrete statement that one could sort of take home and think of as an achievement of integrable probability, so to say. The example relates to the so-called six-vertex model. So the six-vertex model is a wonderful object. It was first introduced into chemistry or physics, I don't know what actually, by Linus Pauling in the 30s. So if you go to Wikipedia, Wikipedia is going to tell you that Pauling was the only person who was awarded 2 Nobel Prizes unshared. Okay, so one was in chemistry, and the other one was the Peace Prize. He was the head of the effort to ban open-air nuclear tests, and that campaign was successful. Actually, that's the prize. But anyway, this is much earlier, and so the model was invented to compute something that can be experimentally measured, called the residual entropy of ice. I'm not going to go into the experiment of what happens. Roughly, as the temperature goes to absolute zero, there is something that remains non-zero, and that's this residual entropy. And so the interpretation that's given to it is that if one looks at the crystallic lattice of the ice, one knows how it looks like. The red big things here are oxygens, and they are connected between themselves by something called hydrogen bonds. On each bond, there is a hydrogen atom, and that atom on each bond can be in one of the two symmetric positions, either close to one oxygen or close to the other oxygen, roughly 2-to-1 ratio in distance or something like that. And then each oxygen has valency 4, so there are 4 H bonds that are attached to it. Right, so what one wants to do is one wants to take a big domain in that lattice and compute the number of possible configurations. That is a very difficult problem. Nobody knows how to solve it. So Pauling said, okay, forget about the three-dimensional structure. Just think of the flat thing. So think of the square lattice with the oxygens and the hydrogen bonds between them. And so we know that near each oxygen there are 2 hydrogens, and that's it. We want to count them. Right? So what Pauling did, he actually said, locally there are only 6 possibilities for the oxygen. The hydrogen, there should be 2 hydrogens next to it, and these are the 6 possibilities. And then he estimated the number of configurations here as 6 to the n, and that gave a theoretical value for the residual entropy that was actually very close to the actual measured value, closer than 5% or something like that. So that's one remarkable computation that doesn't even require the computation, that predicts the value of an experiment pretty accurately. But anyway, the number of configurations is certainly different from 6 to the n. Yeah, I should have told you maybe before that. So this picture is not, I didn't make it. This is a picture from Nature from last year, maybe the year before. Apparently it's a picture from a paper about the experiment where physicists took water and put it under 2 sheets of graphene. So they actually made something like square ice experimentally. They have nice pictures. You can look it up if you want. Anyway, so the 6-vertex model, what is it? So that's the model is that one has a plane domain of the quadratic lattice. Then there are oxygens in the vertices, and then there are these hydrogen bonds between oxygens, and then there are 6 possibilities for every oxygen to have its hydrogens around. And so one generally assigns weights to these 6 types of the vertices and then multiplies these weights. And then that's the weight of the corresponding configuration. If all the weights are 1, then you just count all possibilities. Right? That's what it is. Now, it's more convenient to parameterize the picture by what's known as a height function. So if these 6 vertices are redrawn in the way that's here, then the picture turns into upright paths, actually. And these paths, they can touch, but they cannot intersect otherwise. Okay? So we're talking about enumeration of paths like that. And then the height function is just counting how many paths one has to the right or to the left of some location. So if you travel from the left, then there's 0. Then you cross one path, there is a 1, and then 2, and so on. So that's the height function. That's what I will talk about. So the theoretical progress in the 6-vertex model actually started with Elliott Lieb, who in 1967 computed the asymptotics of the number of configurations on a torus. That was a big breakthrough. That got even closer to the experimental value for the real ice, actually. Anyway, there is a connection of the 6-vertex model to quantum mechanics, to something known as Heisenberg ferromagnet, or the XXZ quantum spin chain. I'm not going to say more about it. If you want, that's not going to participate in my talk later on, but I just wanted to say that there's a large part of physics that sort of cares about the 6-vertex model. The concrete case of the 6-vertex model that I want to consider is rather simple-minded. Namely, it's the following. If I take my 6 vertices and if I give them weights in the following way, well, as written here, 1, 1, B1, B2, 1 minus B1, 1 minus B2, where B1 and B2 are 2 numbers between 0 and 1. Then the random configuration of paths can be constructed in a Markovian fashion. So imagine these paths traveling up and upright, and imagine that you already know how they look below this diagonal red line. Then as a path approaches this line, it has a choice, or it might have a choice, to go right or to go up. And so it does this choice with the flip of a coin, with bias B1 if it came from the bottom, or with bias B2 if it came from the left. And if 2 paths came to the same vertex on the 2 sides, they have no choice but to carry on as they came. Okay, so that's it. So then if you take some initial condition, for example, the quadrant, and then all paths enter from the bottom, then you can just flip coins at each choice, and then propagates. Okay. So it propagates, and then what does one get? Well, before I show you what one gets, I'll say one more thing. So traditionally, the 6-vertex model is not studied in this fashion. The way it's studied is that one takes or in general, statistical physics models, one takes a domain in the plane, and then with finitely many vertices, and that looks at the random configuration there, and then sends that domain to infinity to see what happens. Okay? So the model that I just defined in Markovian way by this propagation can be defined in that way too, even though the way of going to infinity is a little weird. One starts with a rectangle and then makes this rectangle very long and then very tall. But there are other ways to do it. So there is a more traditional way to define this particular measure. On paths, one thing, if you've seen 6-vertex model before, then you would know that the 6 parameters for the 6 types of weights, they actually fall into different regions according to some properties of the model in large-scale limits. And so that only works for the so-called ferroelectric region. But if you didn't know about that, then don't worry about it. It's not necessary. So this is a simulation. All right. So here, paths are entering on the bottom. They are black, and then they use the Bernoullis, and then they propagate. Okay, so then you see that there is some limit shape, frozen circle, which in this case is a cone, probably. And then this picture is not very visible in this resolution, but this is a picture of the fluctuations. So one subtracts whatever the limit shape is, and these are the fluctuations. Okay. So the result, the concrete example that I wanted to have in mind when I will talk about the branching graphs, is the following limit theorem. It says that if I take this model in the square, have my path travel according to these Bernoulli flips, then the height function at large distances scales linearly with the distance, and there is a law of large numbers that's explicit. Here it is. Xy is the coordinate of a point that I'm looking at, and then the variance grows as L to the 2/3, and the limit theorem with some concrete value for the scaled variance leads to the so-called GUE distribution in random matrix theory, GUE Tracy-Widom distribution. So this is maybe expected to people who have seen TASEP or other 1+1 dimensional interacting particle systems, but from the point of view of the 6-vertex model, this is actually a fairly unexpected result, because typically in 2 dimensions people expect logarithmic fluctuations of the height function, but in this particular case it's just not true. Now, a while ago, Guy and Spon, this is a physics paper, predicted that whatever this limit law should be, it should be similar to TASEP, ASEP, and things like that. That roughly saying this is, well, what they said is that this model is in what's called the KPZ, Kardar-Parisi universality class. Not much was known about that class when that connection was made, but since then, people learned how to solve models in the class, and so this is sort of expected to see this limiting distribution, but the values of the law of large numbers and the exact scaling were not known. This slide reminds to those who knows and tells you, if you don't know, that the Tracy-Widom distribution appears as the scale distribution of the largest eigenvalue of a random matrix, of a random Hermitian matrix, with the Gaussian measure in it. So the real and imaginary parts are independent Gaussian whenever they can be, and then the top eigenvalue scales as √2n at large size n. And then if you subtract the law of large numbers, divide by the variance, then there is a law.
There's the minus there in the denominator, you don't really want it.
This thing, yeah, it has to be there, right? That's because, okay, so the, right. So it says, it disappears, okay. There is always a confusion with this minus, because the, if one considers discrete models, then there would be a positive power there no matter what, because the distances are always larger than 1. But in this case, so this is √2n, or 2 roots n, √2n, right? And then there is a total of n eigenvalues. So in the bulk, the distance between the neighboring eigenvalues is like 1 over √10. And so when you get closer to the edge, the eigenvalues spread out further, and so then you get 1 over n to the power 1/6. That's the n to the -6. Okay, so this is the concrete example. It was a result proven a couple of years back, and so I want to now approach that result from some framework. The framework will be that of the Gibbs measures on branching graphs, and I will do that. Meanwhile, let me point out that this is a bona fide integrable probabilistic model. We were able to control the asymptotic behavior of it to a pretty fine scale. It's not achievable by any other methods, as far as I know. It's a member of a universality class, so if this were the first model in the class, it would have given predictions for other ones. And then it connects the subject for some reason to random matrices. That's also not something very expected, I would say. But again, with integrable stuff, it often happens because the algebraic structures are often shared by problems from different fields. Anyway, what I didn't describe at all is the algebraic structure that really leads somewhere, and that's because I want to spend the rest of the talk doing that. Okay. So now I can actually get to branching graphs. The simplest example I want to look at is the Pascal graph. So in general, a branching graph for me is a graph that's z plus graded. So the vertices are split into levels. There is a 0th level, first, second, and so on. The 0th level is always a single vertex. The edges are always between neighboring levels, as you can see here. The edges may be simple or may have multiplicities. They will also have formal multiplicities, which would not be integers later on. But for now, these are simple edges. Each edge has multiplicity 1. Now, the important definition for me is the definition of the Gibbs measure. So the Gibbs measure is a probability measure on paths in such a graph. So this is a path that goes from the root off to infinity. It's random, and the randomness as Gibbs is the following property if the following property holds. If I fix some vertex and condition the path to go through that vertex, then all parts between the root and that vertex have equal conditional probabilities. Okay? So fix a vertex, and then these two will be the same. For a vertex, let me denote that by phi of lambda. Okay. I will also want to have another characteristic of my graph, which is, for reasons I'll tell you later, is called the dimension of a vertex, and that's just the number of paths from the root to the vertex, and so that's the binomial coefficient for the Pascal graph, right? Okay, it's really immediate to see that the Gibbs measures are in one-to-one correspondence with non-negative functions phi of lambda that satisfy this condition. So what is this condition? This condition is saying that the value of a function at a vertex is equal to the sum of its values at the two vertices right above it. Okay? Now, why is that? Well, that's because I can just compute the number, I compute the weight of path going through this vertex in two different ways, just as a phi of that vertex, or splitting it into two pieces going through this vertex to that vertex. Okay? Now, the question for the audience for the next 30 minutes is whether you can give me examples of functions on the Pascal graph that satisfy this property. Okay. If you've never seen this question before, then entertain yourself for 30 seconds. So it's a function on the Pascal triangle such that the value here is equal to the sum of the two values here and here. Okay, I'll give you one example. Function identical equal to 1 on this edge of the graph and 0 everywhere else. Okay. Say it again?
2 to the minus.
Great. This is a wonderful example. So the function equals 1 here, 1/2, then 1/4, 1/4, 1/4, 1/8, 1/8, 1/8, 1/8, and so on. So 1/2 to the level. Yeah, that's indeed an example. And that example is easy to generalize, actually. You can consider p to the k, 1 minus p to the l, right? Where k and l are the distances from the vertex up and down. Okay, and if p is half, then that's the example that Lionel suggested. Wonderful. Now, is this all? Okay. Now, before I answer that question, so I'm trying to classify Gibbs measures on the Pascal triangle. Now, so before that, I'll spend 1 minute on the question that people should ask themselves, especially mathematicians sometimes, which is who cares? Okay, why should we really care about the Pascal triangle? All right, so an attempt for an explanation. This is a usual definition. So if you have a sequence of zeros and ones, which is random, it's called exchangeable if the distribution does not depend on the order in which you observe it. Okay, and exchangeable infinite sequences of zeros, ones are in one-to-one correspondence with the Gibbs measures on the Pascal graph. And the correspondence is very simple. This is what it is. if you compute the probability of having a sequence that has k zeros and l ones in whatever order, you assign to it the value phi of the vertex. And you'll see that the equation that this phi satisfies is exactly this equation. And so this is in one-to-one correspondence with the Gibbs measure. And then the question is the following. Somebody gives you a bag of zeros and ones and says, OK, tomorrow, and the bag has, I don't know, 1,000 things. And then the person says, OK, tomorrow I'll bring you another bag. And if you guess how many zeros there within 3%, I'll give you, I don't know, whatever, $1 million, something like that. OK, so how should one predict? Is it reasonable to think that zeros and ones are really independent Bernoulli flips? OK, are there any examples? So this is really the beginning of Bayesian statistics. And if you try to see what the origins of the Bayesian statistics were and what were the arguments of proponents of that, then the only real statement that I was able to find is this statement. Okay? So this is known as the Finetti's theorem. It's pretty old. Chances are you've seen it somewhere. So it says that Gibbs measures on the Pascal graph are convex combinations of the ones we already know. P to the k, 1 minus p to the l. It also says it's not reasonable for the bag of zeros and ones that you were given to think that they are independent Bernoulli flips. There is actually this convex combination, which is a probability distribution on the bias. And that's really the pre-image of the prior distributions in the Bayesian statistic, right? So you should really plan for it because it's there. Otherwise, you won't get your $1 million. All right, so the picture that I like to keep in mind when I'm talking about it is the following. Now, this is my Pascal triangle. It goes off to infinity. And somewhere at infinity, there is this segment 0, 1 on which these measures live. And this is the boundary of my graph. There is an exact sense in which is the boundary, but think of it as just a term. And so if you take a point on the nth level, and then you consider all paths between the root and that point, uniformly distributed, that's a Gibbs measure up to that level. And if you send this point to infinity now, then if you do it in the smart way, then this measure on paths will converge to a limit. Okay? And the smart way would be here just splitting the segment into parts whose ratio is p and 1 minus p. All right, so we think of these points as sort of approximating this ideal boundary that sits somewhere above. All right, so that's it. That exhausts the Pascal triangle example. And now I will go into more dimensional examples. Okay, these two are already infinite dimensional, actually. And I'm very happy because the previous talk set me up for a good discussion of one of them. So you see, these are the graphs. They are built from Yann diagrams. Again, these are staircase-like structures with 1-by-1 boxes. This one just has plain edges. So multiplicities are all ones on the edges. And the green here is the dimension. That's the number of paths from the root to that vertex. Okay? Now, this here has multiplicities. This is known as the Kingman graph. And so this graph is more understandable, actually. Well, OK, this is understandable as a graph. But the algebraic origin of this graph is more understandable. This is the branching of permutations by their cycle structure. See, if you add up these numbers, so that's the number of paths, then you see this is 6 here, and it's 24 here. So paths from the root to the level corresponds to a permutation. And then the partition here, if you read the number of boxes in the rows, that gives you the cycle structure of that particular permutation. And then the edges correspond to the fact that if you take a permutation of 1, 2 up to n plus 1, and then project it to a permutation of n by killing n plus 1 in whatever cycle where it sits, then you will get, if you start with a conjugacy class, then you will get a combination of several conjugacy classes, and that will happen with this branching. Okay. All right. So this comes from representations of the symmetric groups I'm not going to talk about, but one thing I will mention is that even though these numbers do not add up to 24, their squares do. Okay, and that's a nice fact. If you haven't seen it, it's sort of a piece of recreational mathematics proving that these numbers squared add up to the corresponding factorial. Okay, it's not a trivial statement. It's not too hard either. It's pretty nice. So I won't talk about this example because I'll have a later example that's more powerful by that. But I'll say something about the Kingman graphics, especially because there was a talk before that. So here is a classification of Gibbs measures on the Kingman graph. So again, the Gibbs measures are measures on paths such that if you fix a vertex, then whatever leads to that vertex is equally distributed. This is a fairly deep theorem proved by Sir John Kingman, who is considered the founding father of population genetics. And the fact is the following, that the role of my point going to the boundary in the Pascal graph is now played by a sequence of partitions, or Yann diagrams, that grow in a prescribed way. And that growth is that the rows grow proportionally to the total number of boxes in that partition, and the coefficients of the proportionality are fixed. And these partitions label the Gibbs measure. These are the extreme measures, and all the other ones one gets by convex combinations of these ones. Okay? So that's the statement. Curiously, if one starts with the most natural measure on the graph, which is just counting the number of permutations with the corresponding cycle structure, that measure is not extreme. It's an example of the Poisson-Dirichlet process that we talked about, a very particular one. So what does it mean that it's not extreme? It means that it's a convex combination of these ones. So it produces a probability distribution on alphas. How should one get that probability distribution? It's a remarkable distribution. So one way of getting it is the so-called stick breaking process. The stick breaking process works like that. You start with a stick of length 1. You throw a uniform point there. It splits it into 2. You break it, and then you put one piece aside, take the other piece, and then play the same game. Put the uniform point, break, place it aside, and so on. And then you get a lot of pieces of that stick. Then you order them, and that's the random alphas. Okay. Why is this such a wonderful distribution? It seems to be fairly simple. Well, it comes up in a variety of setups, and one of those is number theory. So if you take a random integer between 0 and 1,000,000, and then split it into prime factors, and then look at the log sizes of those prime factors, then those log sizes will follow, as the million goes to infinity, the same Poisson-Dirichlet distribution than this one. These objects usually are not considered related to something like random matrices or TASEP or something like that. And so my reason for bringing this up was that they really should be. They live in the same world. Okay, my examples will sort of grow in complexity. So I will eventually want to get to the 6-vertex model. So I will want to close it by coming back to the 6-vertex model and explaining how the Gibbs measures on the corresponding graph help to get the limit theorem that I started with. But meanwhile, my next example is the Gelfand-Zetlin graph. What is the graph? I'm not actually drawing the graph. So this picture here, which one could think of as a tiling of a half plane with rhombi of 3 types, or if you turn on the 3-dimensional vision, you can sort of see here a 3-dimensional staircase that goes down. So this up to level n is a path in my graph that goes from the root to level n. So at level n, I have positions of my vertical tiles at some horizontal n. So this is my level n. Okay. The 2 levels, the 2 vertices at neighboring levels are joined by the edge if the corresponding coordinates interlace, and so that's visible in the picture. The vertical rhombi interlace when you go between the levels. And the multiplicity on the edge, I could put just once, the plane ones, the plane edges, or I'll do something more general, actually. It's useful to do something more general. which is I put a number that depends on the level and then raise it to this power, which is always positive if the interlace. This is a rather powerful example. So, okay, let me go step by step. The first question, the dimension, the number of paths between the root and the given vertex. That was the binomial coefficient in the Pascal graph. That was the number of permutations of a given cycle structure here. That was the reducible, the dimension of the reducible representation of the symmetric group here that I never gave you, but there is a formula. So in this case, it's given by this formula. So this is the ratio of two determinants. It's known as the Schur polynomial, and this is a remarkable quantity in itself. It has a representation theoretical origin. One can interpret it as characters of certain irreducible representations of UN, but one shouldn't really care about that. Think of it as an explicit formula. So the first sign that your graph is good is if you can compute the dimension. Okay? If you can compute the number of paths from a root to a point, that's already pretty good. Okay, so this is clearly an overloaded slide. I don't expect you to look at every corner of it. It contains more information than needed. This is a theorem that gives a classification of all Gibbs measures on the Gelfand-Zetlin graph. Just follow with what I said, and if you want, you can look at other things a little later. I only need to define phi. Remember, phi was the probability of the path going through a concrete vertex. Okay? So the description of phi is obtained in the following way for an extreme Gibbs measure. One takes some function and decomposes it into the Schur polynomials that I put here. These Schur polynomials form a Fourier basis for functions in n variables. So if I have any function, I can decompose it. And then the coefficients will be the probabilities I want. The function that is being decomposed is a function that's fairly simple. It splits into a complete product of linear factors in the numerator and denominator. The exponential is just a limit of these factors. Okay? And then the parameters of the measure are the coefficient in these linear factors. All right? There is also a way of describing this in the same way I did it before by growing a Yann diagram to infinity. And so this picture gives an explanation of how that happens, but I'm not going to go there. It's just, I mean, these numbers have an interpretation as the rates of growth of rows and columns of some picture. Okay? So this is a deep fact. It is also equivalent to a representation theoretic statement about classifying characters of an infinite dimensional unitary group. Let me point out to a few things about this theorem that will repeat themselves as I go to the 6-vertex model. Okay? So what are they? First, as I said, the way to get to the measure, if you actually want to compute something, is you take something, you take an expression and you decompose it onto a good basis. That good basis is an orthogonal basis. In this case, it's orthogonal on the torus with respect to the measure that's given by the square of the van der Monde determinant, the absolute value of that. The fact that this thing here splits into a product of simple factors. This is a major simplification comparing to, for example, a finite n problem. This is a simplification that happens only as one goes to infinity, and this is sort of a key feature why infinite dimensional representation theory is sometimes simpler than the finite dimensional one. There is something happening that the functions you need to consider are only products of linear factors. Okay? That we'll keep in mind. Now, what I told you here holds for my multiplicities being ones, so the edges being simple. But the same formulas give actually Gibbs measures for arbitrary parameters AIs, except for sometimes they will not be extreme points. Actually, the problem with arbitrary AIs is not solved. The boundary of this graph is not known. It's only with ones. Now, the Pascal graph that I started with is a tiny subgraph of the Gelfand settling graph. It corresponds to these sequences being zeros and ones. If lambdas could be only zeros and ones, that's the Pascal graph. And one of my factors here carries the parameter p, that segment for the Pascal graph that was there. Okay. And then if you like symmetric functions, then the summation formula is actually known in symmetric functions as the Cauchy identity for the Schur polynomials. But let me leave it at that. So this Gelfand settling graph, the reason I brought it up is that it is really a major source of integrable probabilistic models. The exclusion processes, the totally asymmetric exclusion processes that I mentioned before, come up from this graph, actually from some sort of a dynamics on paths of this graph, not unlike the diffusions that we've heard about in the previous talk. Other things too, so the plane partitions or random surfaces, they are, well, you can see them in this picture, but with certain weights, they fall into the framework provided by that graph. And then random matrices actually also rise from this graph in a certain limit. In any case, there is a group of models that just sort of fall into the neighborhood of this object. Okay. They are all, so to say, free fermionic, so they're all computable by determinants, and that's the reason to me that they were all analyzed to different degrees of detail. All right, so now I'm in the final stretch. I want to return to the 6-vertex model, to the example that I started with. So for the 6-vertex model, again, I'll start with a picture of the path between the root and level n. So this is the path. Level n will encode the positions of the vertical edges at the horizontal level n. So these are just n numbers. They're ordered, strictly ordered here. Again, the edges go between the n tuples, n and n minus 1 tuples that interlace. That's exactly the same as in the case of the Gelfand settling graph. Nothing changed. But the multiplicity changes. So the multiplicity of such an edge will now be the 6-vertex weight of this strip of width 1. So I draw a piece of this picture between level n minus 1 and n, and then I take the product of vertex weights where the vertices are the 6-vertex vertices, right? So with the, okay. And now I want to study all Gibbs measures. Okay, can I do that? No, but I can do something, and that ends up being useful. So let me try to repeat some of the things I did for the simpler graphs. So first, I'm going to reparameterize my weights. You know, these A's and B's and C's, they're easy to write, but they're not convenient. Because really, the Gibbs condition on this graph only depends on 2 parameters, not 6. It only depends on this point in the projective space. Moreover, these 2 parameters, one of them plays a different role from the other one. One of them is called a spectral parameter, and not much depends on it in a way. You'll see in the next slide. And the other one is sort of more relevant. It's Q. It's the quantization parameter if one compares it to the free fermionic model. It's also good, actually, to allow vertical edges to have multiplicity. So in the 6-vertex model, it's not allowed. The paths cannot share the same vertical edge. But if one takes something known as the highest spin 6-vertex model, then it is actually allowed. And so here is a particular parameterization of weights that I choose. The blue m's and m plus 1s here are the multiplicities of the edges. And the m is allowed to take some finite set of values. So in particular, if the spin parameter is half, then this is the 6-vertex model. So once that boring preliminary work is done, I can look at the dimension. So the dimension, what is the dimension? The dimension is the total weight of all pictures like that once I fix the top row. And it's computable. That's the first sort of good sign, or the sign of integrability. And this is a formula. Okay, the formula may not look too appetizing to you, but it's not a bad formula. So this is a symmetrization of a certain rational expression. It's pretty explicit. So U's are the spectral parameters chosen along the n rows. If Q and S both are 0, then this returns to this formula here. Okay, the symmetrization becomes a determinant, and so one goes back to that thing. Moreover, these expressions, similarly to the Schur functions, they are a Fourier basis. They are a basis in all rational, all Laurent polynomials in these variables, actually symmetric ones. There is an orthogonality relation on them, and so one can take something and decompose it on this basis and read off the coefficients. Okay? And the statement is that if one does that, then these coefficients will produce a Gibbs measure on the graph. Okay? So if one starts with a function with a split product, somewhat similar to the previous one, and then decompose it in this way, then the theorem says that this way one can get Gibbs measures. I don't know if they're extreme Gibbs measures, but they are Gibbs measures. And the original measure that I started with, the one that produced a cone through a simulation, it's an example of such a measure. You know, there was this simple-minded description of, this one. No, not this one. This one. Building the paths in the Markovian fashion, the one that produces that picture. So that's one example of such a Gibbs measure. Okay? Now, doesn't look like I've done much, because I just gave a very fancy interpretation for a very simple object that I started with. And the good thing is that I now have a lot of such objects. And so here is a baby trick that I haven't seen anywhere to work actually as spectacularly as here, which is if you have two measures on the same probability space, they're probability measures, so they add up to 1, then you can interpret the statement that let's say the second measure adds up to 1 as the fact that the average of the ratio of the two measures averages to 1. So you get an observable out of the two measures, which is their ratio. So if you have many measures, they add up to 1, and they're somewhat similar in the sense that their ratio is simple. It's an observable that carries information. Then you get many observables. They average to 1. They give you relevant information. And that's exactly what happens. So this is my original measure. So it comes from decomposing this split product with one parameter being non-zero. Now I add another parameter being non-zero. I take the ratio. And that ratio ends up being a Q correlation function, something that has a very clean probabilistic meaning. Doing it a little higher, adding more parameters gives higher correlation functions and eventually leads to the limit theorem that I stated before, the convergence to the Tracy, the central limit, not really the central, but the Tracy-Widom limiting distribution and the law of large numbers before that. All right, so there are other examples that I haven't covered of integrable probabilistic models that fall into other branching graphs. Okay. So branching graphs, where do they really come from? In the examples that I showed, I didn't really stress where they come from, but originally they came from representation theoretic objects. Maybe I go to the next slide. Something like symmetric group with permutations growing, or unitary groups with unitary matrices growing, or something like that. And these objects, they give nice branching relations. When you restrict to a smaller one, the object splits, and you can compute things in this way. So there are not so many symmetry groups for which this can be done. There are only that many simple E groups. But then over time, representation theorists and people around representation theory learned how to deform that, how to add parameters into these symmetry groups. Even though this is no longer a unitary group, this would be something related to it. and affine Hecke algebra, double affine Hecke algebra, things that you may have heard. These are essentially classical symmetry groups deformed in such a way that certain integrability properties stay there. Okay? So this still leads to branching graphs. It's adding parameters to branching graphs. And so this branching graph here actually relates to something called quantum groups, which are not really groups, but a Q deformation of the symmetry groups. And so once the branching graph is there, there is a natural question, at least natural to me question, of classifying the Gibbs measures on the graph. And if the graph has nice properties, then these Gibbs measures can be handled to an extent. Okay? In the Pascal graph case, they can be handled completely. In the Gelfand-Zetlin graph case, this is much harder, but still can be done. But even finding sufficiently many examples of the Gibbs measures is beneficial, as I tried to show in the 6-vertex model. Right? And then, if one can really locate such a sort of nice branching graph, then there are various tools to extract more simple-minded objects that should be, and sometimes are, of interest to, just from a mathematical physics point of view or from a probabilistic point of view. It's easy to say that an object like that shouldn't really worry a probabilist that sees that. But if you look at an object like that, and this is a sort of describes something very big on this graph, but if one zooms in onto these particles, the leftmost rhombi in each level, and then one runs some sort of a Markov dynamics on this object, then these leftmost rhombi start doing TASEP. Okay? And TASEP is one of the basic models that interacting particle systems people care about. Okay? But at the bottom, there is sort of a much larger object that carries the algebra. Okay? So I guess the point that I'm trying to make is that if one manages to uncover this larger object, then it does serve as a source of interesting solvable models. And looking at these sort of elephants, if you want, that hidden somewhere behind is beneficial. If you can understand them, then they give interesting things to you to look at. All right, so thank you very much for listening. That's all I wanted to say.
Questions? Do you have a book that explains all this?
No.
Are you writing on?
No, but I have 3 sets of lecture notes from summer schools that are all on the archive, and they contain whatever I said today. They cover. So.
Great. Any more concrete questions?
Is there some classification of all of the branching graphs, or do we expect to keep discovering more of them?
It's not. It's a hard question. I mean, any branching graph wouldn't do. You need to be able to compute something about it, right? So you want to compute this dimension. I mean, you want to have some sort of a formula. And no, I don't think there is a classification. There are representation theoretic objects that are known that produce some branching graphs, and some are better for probability than others. But I think there are more to look for. I mean, maybe I should also say that the reason I stress the branching graph is that there is a very well-known problem in statistical physics, which is classify all translation invariant Gibbs measures for whatever. Okay, for tiling models, for 6-vertex models, and for so on. So this is always a difficult problem. I mean, it's very difficult actually. But once the problem is put onto a branching graph, the fact that it only goes to infinity in one direction makes the problem simpler. Okay, and that's one reason why sort of having the Z+ grading helps. But again, I don't think all good ones have been found. No, I don't believe so.
We could view even the solution of the two-dimensional easy model as based on this principle of writing it as a sequence of lines.
Yeah, that's a natural way to algebraize something, right? I mean, you need to start from somewhere. If you have an object that's translation invariant, okay, what do you do? Thank you.
Other questions? Let's thank you.
Okay, so the first speaker in the after Birnbaum lecture period is Sébastien Bubeck, who is going to talk about local max cut in smooth polynomial time. Sébastien is local, he's Microsoft.
Yes, thanks, Ed. So I'm going to tell you about the local max cut problem. So this is joint work with Omer Angel, Yuval Peres, and Fan Wei, who was my intern this summer. So it's a problem at the interface of computer science and probability theory. And it goes like this. So let me start by giving you the background. So the story begins with a graph. Okay, so G, that's the vertex at the edge set. And we have a weight function on the edges. So that's defined from E to R. So the max cut problem is defined as follows. So max cut, it's an optimization problem, a combinatorial optimization problem. We're trying to maximize over all sigma in the hypercube, minus 1, 1 to the n. So we're going to identify the vertex set with the integers from 1 to n. And what we want to maximize is the following. So you should think we're trying to partition the graph into a set of vertices which are assigned to minus 1 and a set of vertices which are assigned to plus 1. And we want to maximize the cut between those two partitions. So here you see this vertex. It has different weights on these edges going across the cut, and we want to maximize this sum of weights. So formally, what we want to do is we want to maximize the sum over all edges ij in E of the weight wij, and we get wij if we cut this edge. So when do we cut this edge? Well, we cut this edge if the product of the sigmas is minus 1. Okay, so we cut, so we get 1 minus sigma is sigma j. Right, so this gives me a 2 if they are in different partitions, so I rescale by 1/2. Good. So the max cut problem has to find the sigma that maximizes this. Okay, so this is a basic primitive for many, many problems, in particular in graph partitioning. And maybe more importantly in this talk, it's really a central problem in computer science because it's NP complete. Okay, so if there was a polynomial time algorithm for this problem, then there would be a polynomial time algorithm for a vast category of combinatorial optimization problem, all the NP, all the problems which are in NP. Okay, so this is very important. What we're going to look at in this lecture is local max cut. So in local max cut, instead of trying to find the global maximum, we're just going to try to find a local maximum. Okay, so find a local max. Where local is with respect to the Hamming distance, right? So two sigmas are neighbors if I can go from one to the other by just changing the value at one vertex. Okay, so that's what we're going to look at. So this problem is just as central as max cut, but for a different class of optimization problem, namely for local search problem. Okay, so the first motivation to look at this is that it's what is called PLS complete. And I will tell you what is PLS. So PLS, that means polynomial time local search problem. Okay, so polytime local search. This is essentially, okay, I won't define it formally, but this is essentially the class of combinatorial optimization problem for which you can run a local search, okay, in polynomial time. And what we want in this class of problem, we want to find a local maximum. And what this sentence is saying, the fact that local max cut is PLS complete, it says that if there was an algorithm to solve local max cut in polynomial time, then there would be an algorithm to solve any local search problem in polynomial time. Okay, provided that basically you can run a local search. Okay, so this seems very highly unlikely because we are not putting any structure in this class of problem. Of course, just as NP-hardness, we don't know how to prove that there does not exist a polynomial time algorithm to solve PLS problems. But this you can think about it as some sort of hardness of local max cut. Okay. So that.
Local search means you're just looking to a vertex and its neighbors.
Yes, it means that you have a definition of a neighborhood, and that given a potential solution, what you can say is you can give another solution which is neighbor to it and which has a better value.
But do you enumerate all the solutions, or you're happy with just one of them?
You're just happy with one of them. You just want to find one of them. Yes. So the point is, this is a hardness result, but in practice, this is supposed to be an easy problem. You've never heard someone saying that it's a bottleneck to find a locally optimal solution. Right? Everybody thinks that it's easy to find a locally optimal solution. So it's sort of strange, this result, because it's saying that something that everybody solve every day is actually hard. So the point of the talk is to look at a way to understand this discrepancy between real life and theory. So what we're going to look at is smoothed complexity. Okay, so smoothed complexity. So this was introduced by Spielman and Tang in 2004. And let me also say just who introduced the PLS class. So this was done by Johnson, Yanakakis, and Papadimitriou in 88. And the fact actually that local max cut is PLS complete. This was a later paper by Schaeffer and Yanakakis in 92, I believe. Okay, so what we're going to look at is smooth complexity. So what does it mean? So again, in real life, those problems are easy. Okay, so one issue is that in the worst case, there are, okay. So smooth complexity is going to be the following. We're going to add a little bit of noise to the weight function. Okay, we're going to say, okay, maybe the worst weight function is hard, but it's hard because of a very special structure. And if you just add a little bit of noise, then it's going to remove all the hardness in this weight function. Okay, so smooth complexity is what if we add a bit of noise to W. Can we show that in this case, this problem is solvable in polynomial time? And we're going to look at a special algorithm, which is the most natural one, local search. Okay. So it's a natural algorithm. It goes like this. So let me denote by little h of sigma for this value. So the natural algorithm is just you add some sigma, and there is some vertex that you can move to improve the value of h. Then you just make this move, and you continue until you reach a local max. Okay, so while sigma not locally opt, not local max, find v such that h of sigma minus v. Okay, so sigma minus v, I hope this is clear, is just sigma is the same value as sigma for all vertices except vertex v, and for vertex v, we change the sign. Okay, so in terms of the partition, it just means we pick vertex v and we move it to the other side. Okay, so we find a v such that this is strictly larger than h of sigma, and set to sigma, we put sigma minus v. Okay, so this is just a very natural local search algorithm. And what we're going to show is that if you add a little bit of noise to the W, then this algorithm will terminate in polynomial time. Okay, that will be the punchline of the talk. Okay, so this is called, sometimes it's called the flip algorithm. And just to be clear, it's a family of algorithms. So there are two things that you need to specify to actually run this on your computer. The first thing is what is the starting point. Okay, so this is not specified. So you can think maybe I'm taking a uniformly random point. That's one possibility. There could be other possibilities. So the starting point has to be specified. And how do you choose among, if there are many V's for which this improves, you have to choose one of them. So which one do you choose? Okay, so again, you could choose one of them at random. Okay, there are many things you can do. So we will say that an implementation of flip, that means it's running flip with a certain way to decide the starting point and a certain way to decide among several moves that improve. Okay, that will be called an implementation of flip. And the theorem that we're going to show goes like this. So the problem is, let me just say this, there exist W's for which this algorithm will take exponential time. Okay, so this does exist. And the point...
Exponential, you mean exponential in n?
Yes, exponential in n. That's what I mean. Okay, and you can think we are going to rescale everything so that the weights are all between -1 and 1. Okay, so it's not about the weights. Okay, so the theorem that I want to tell you, so that's with Omer Angel, Yuval Peres, myself, and Fan Wei, student at Stanford. So it goes like this. So now we're going to have random variables on the edges. So let xe for e in capital E be independent random variables. Let's say in -1, 1. So these random variables, I think of them as the weight function plus some independent noise. Okay. If you want, instead of -1, 1, it's fine if you prefer Gaussian to think that these are standard Gaussian. That's the same thing. We just need finite variance for everything that I will tell you. Okay. So, and let me define h, capital H of sigma is going to be -1/2 the sum over ij in E of xij, sigma I, sigma j. Okay? So what we're trying to do is we're trying to maximize this capital H, right? Little h is the same thing as capital H up to a constant, which depends on the sum of the weights. Good. So then, with high probability, any implementation of flip okay, so no matter how you choose the starting point, no matter how you choose the improving move, any implementation of flip terminates in a certain finite number of steps, in some polynomial number of steps. Okay, so it's going to be n to the 15 steps. So as stated, there is something missing, because right now, I didn't say anything about these random variables. In particular, they could be point masses, right? So it could be the worst case, just again. So I need to assume something about the fact that there is noise in this process, and we'll do this by saying that they have a density with respect to the Lebesgue measure, and this density is bounded. Okay? So let's assume that let phi be the maximal density of xe with respect to Lebesgue. Okay, so this is a measure of smoothness. It's saying that it cannot be too concentrated. All right? And this bound is going to depend on phi also. So it's going to be phi to the 5. And a little caveat here is that in this case, we also have to assume that G is a complete graph. So G is the complete graph. Okay, so what it means, in some sense, the assumption that G is a complete graph, note that I assume that those random variables are independent, right? Not IID. So for instance, I have this graph. I could put a much smaller noise on the non-edges, right? I could imagine, okay, I have a complete graph, which means that I have a 0 weight on non-edges, and I need to also smooth the non-edges. Okay, so I need to also add noise to the non-edges, but I could add a much smaller noise than on the other one. Okay. When Spielman and Teng introduced the concept of smooth complexity, what they were looking at is also a local search problem, actually. They were looking at linear programs, LPs, and at a specific local search algorithm for linear programs, which is a simplex algorithm. And just the same story as for the local max cut, it was known that the simplex algorithm can take exponential time to reach a local max of a linear program. For linear programs, local and global are the same thing, right? So it was known that the simplex could take exponential time, and what they looked at is they said, okay, in practice it seems to work really well, so let's see how it would behave on a random instance when I had a little bit of noise. And what they proved is exactly a similar statement. Okay. And in their case, they had to do the same thing. So in the case of a linear program, instead of a graph, you have a constraint matrix, and they had to smooth every entry of the constraint matrix. So even if the constraint matrix was sparse, once they smooth it, it was a non-sparse thing. Okay, so we have the same issue. Good. So now I want to tell you about the proof of this result. And let me mention that what was known before. So there is a very nice paper, which is the starting point of our work, by Etscheid and Roglin in 2014. Where they showed that the flip algorithm stops in n to the log n step. Okay, so n to the O of log n bound. All right, so this is quasi-polynomial. This was for any graph. Okay, so that's one thing that they have, which is stronger than us. But again, there is this discussion that you can add a smaller noise to the non-edges. And the conjecture that we make is that this n to the 15 is just an artifact of our proof. So I think we should be able to almost see the entire proof. The conjecture is that in fact, it should be quasi-linear. Flip is quasi-linear. So this is vastly beyond our current technique, but certainly simulations seem to make this believable. Okay, so this would mean up to some log factors that the number of steps is just linear in the size of the graph.
It doesn't say anything about the feed.
Yeah, let's say, yeah, no, I don't want to make any claim about the phi dependence. For instance, these simulations, I ran them with Gaussian weights. Okay, good. So the first thing that I want to say, let me see how to start. Yes. Okay, so I'm going to introduce a definition. So a sequence of moves, L, which is V1 up to VL. Okay, so the flip algorithm is producing a sequence of moves, a sequence of vertices that are changing, side of the partition. So a sequence of moves is going to be called epsilon slow, is epsilon slow from a starting point sigma naught if the following holds. So the improvement that I get at step I, okay, so I look at h of sigma I plus 1 minus h of sigma I. So I start from sigma naught, then I get sigma 1, sigma 2, etc. as I move my vertices, right? So sigma I plus 1 is just sigma I, or let's say sigma I is just sigma I minus 1 minus Vi. Okay, so when I move from one configuration to the next, I just flip one vertex. And I'm going to say that the sequence of moves is epsilon slow if at every step the improvement that I get in total value is just epsilon. Okay, so this is going to be positive, but smaller than epsilon. Okay, this will be called an epsilon slow sequence. And what we want to say is that you cannot have long sequences which are epsilon slow. So I claim that it is enough to show with high probability that there does not exist epsilon slow sequences with, let's say, I have to tell you what are the parameters L and epsilon, with, let's say, L, which is of order of n, and epsilon, which is something polynomial in n, 1 over n to the c. Why? Okay, so let's assume that this is the case. Why? So let us assume that there does not exist epsilon slow sequences, which are long and do not improve. Then what happens? Then if I do L times 1 over epsilon step, okay, that's the total number of steps that I do. Then after that many number of steps, I have improved by 1. Okay, because I have done 1 over epsilon sequences of length L. Each sequence of length L improves by at least epsilon. Okay, so L times, when I have done that many number of steps, I have improved by 1. But the total maximum that I can reach is n squared, right? Because I have assumed that the weights are bounded. So after n squared times L times 1 over epsilon, which is, we just said, it's like n to the 3 plus c. After that many steps, I have to stop. Because otherwise, if I could still continue, I would reach a value which is higher than the total maximum, than the global maximum. So I just need to show that there are no epsilon slow sequences. Good. So now we're going to bring in linear algebra in the picture. We're going to write exactly what this improvement looks like in terms of the edge weights. So let's look at this. So let's look at h of sigma minus v minus h of sigma. Okay, what is this? So I'm just flipping vertex v, right? So in this sum, all the edges that do not include v, they do not change. The value do not change for the sum end. But for the one where v is either I or j, what do I get? I get that the sign changes, okay, and I have a minus here. So I get once this term. So what this is saying is I get the sum over all u's such that uv is an edge of what? Of xuv times sigma u, sigma v. Okay. So I get a minus 1/2 minus minus 1/2. Okay, so the 2 1/2 becomes 1, and I get exactly this. This is exactly h of sigma minus v minus h of sigma, which I'm going to write as the inner product of x with some vector alpha. So this vector alpha, what is it? It's these things, sigma u, sigma v. So this is a vector in z to the e. Okay, and we can write exactly the coordinate of this vector. What are they? So alpha of uv, this is sigma u, sigma v. Okay, v again is a moving vertex, and alpha of, let's say, uw, where neither u nor w is v, this is 0. Okay, if v is not in uw. Okay, so I'm just saying that the improvement at every step, if some linear function of the edge weights, which makes sense, and this is this particular linear function. Okay. So now I'm going to use a probabilistic lemma, which is just a change of variable. So this was proven by Etscheid and Roglin in their 2014 paper. It goes like this. So let alpha 1 up to alpha k be some vectors in z to the e. Okay. What I want to look at is the probability that the corresponding sequence of moves is epsilon slow. Okay, so I want to look at the probability that for any I in 1 through k, if I look at this inner product, alpha I times x, this is in 0 epsilon. Okay, recall that this is what I care about. I want to show that there does not exist epsilon slow sequences. So for a given sequence, I get a given sequence of alphas. And in this lemma, I'm looking at, for a given set of alphas, what is the probability that the corresponding sequence of moves is epsilon slow? That every step, I don't improve by more than epsilon. And what they show is that this is bounded. So let me assume also that those guys are linearly independent. So let alpha 1 up to alpha k in z to the e linearly independent vectors.
And you fix sigma 0 now.
No. I mean, yes, but okay, these are just given sets of alphas. So they depend on sigma naught, but okay. This could be any alphas. Yeah. So these are just a given set of alphas. This is bounded by phi epsilon to the k. Okay, phi, remember, is the bound just on the density. Okay, this makes a lot of sense. Just, you see, if these things were independent, actually probabilistically independent, then yes, every one of them would be, the probability that one of them is in 0 epsilon is something which, a function of epsilon, some linear function of epsilon. So when I get that they are all in 0 epsilon, I get epsilon to the k. And what this is saying is, okay, those guys are not actually independent, but assuming algebraic linear independence between the vector, give me some sort of probabilistic independence. And it's not a deep result, it's just a change of variable. Okay? So let's see how to use this now. So what is the naive bound that we get out of this? Okay, so as Yuval was saying, now we need to be a little bit careful because we want to show that there does not exist an epsilon slow sequence from any possible starting point. Okay. So what is the probability that there exists a starting point and a sequence of vertices, which is epsilon slow? That's the thing that we want to show that goes to 0. Okay, that there is no way to only make a small improvement. So this is bounded by the following. So I can do a union bound over sigma naught. Okay, so I have 2 to the n possibilities. I can union bound over all the sequences of moves. Okay, how many of them do I have? Well, for each of the L possibilities, I have to choose a point between 1 and n. Okay, so I have n to the L. And then by this lemma, what do I get? I get phi epsilon to the rank. The rank of what? The rank of the corresponding moves, the corresponding alphas. So more precisely, what is this rank? So the rank, I define it to be the minimum over all sigma naught and L of the rank of alpha 1 up to alpha L. Where these alpha 1 to alpha n, they correspond to starting from sigma naught and doing the sequence of moves L. Okay? So this seems like maybe not such an easily tractable quantity, but we'll see that it is. The alphas, okay, so yes, so at least if you don't care about this, they have to be, because you cannot visit twice the same state, because you keep improving, so you cannot come back to the same state. Okay, good. So let's see. So we want this to go to 0. Okay, we want this to go to 0. So if the rank was always of order n, we would be done. So if the rank is, let's say, omega n, then done with epsilon equal poly n. Right? You see that if the rank was of order n, some constant, 0.1 times n, then I can just take epsilon to be 1 over n to the 100, and this term will kill the 2 to the n, and it will kill the n to the l. Okay, where n to the l is something like n to the n. Okay, so if the rank was omega n, we would be done. Okay, the issue is that this is not true. Okay, not true. So the first idea is to do an improvement. So there will be two ideas. One idea is to do an improvement of the stupid union bound of 2 to the n. And the other idea is going to be to do an improvement over this rank, to not look at the worst possible rank, but to look at the rank of good subsequence of moves. So let me try to make this more precise. The first lemma, so improvement 1. So let's call this star for the naive bound. So improvement 1 to star is going to be the following lemma, which will allow us to replace this 2 to the n. Okay, because this 2 to the n is really annoying because then you need the rank to be linear in n. Okay, so it goes like this. So fix L. Then I claim that the probability that there exists sigma naught such that sigma naught L is epsilon improving, is epsilon slow, sorry. This thing is bounded by some constant times n over epsilon to the number of distinct vertices in L times constant phi epsilon to the rank of L. Okay, and the rank of L is just defined as the minimum over all starting point of the rank of the corresponding sequence of moves. So you see the difference with here is that I replace 2 to the n by this n over epsilon to the number of distinct vertices in L. So let me call this number, we will call it S of L. Okay, that's the sparsity in some sense of the sequence, the number of distinct vertices. Good. So the proof sketch. So in words, what we're going to do is that we will, in words, what this lemma is doing, it's a quantization of the external field. Okay, so it goes like this. So let's look at the picture. So we have these guys. So these are the -1, these are the +1. And within them, there are the guys that are actually moving. Okay, so these are the moving vertices. Moving vertices in L. Okay? There are only S of them. Right? That's the number of moving vertices, and many of them are non-moving. What I want to avoid is doing a union bound over the initial spin of all the guys who are non-moving. In fact, the guys who are non-moving, how do they affect, the picture? So let's say we have this guy who is moving, V. He has some interaction with the non-moving vertices, but the only thing that I care about is the sum of those interactions. When I take this vertex and I move it here, okay, whether or not this is between 0 and epsilon depends on what happens inside, and depends on this external field only through the total sum. Okay, so only thing that matters with respect to sigma naught on the non-moving vertices. So the only thing that matters with respect to sigma naught on the non-moving vertices when considering if the move of V is in 0 epsilon. Okay, so I'm trying to decide if when I move vertex V is the improvement between 0 and epsilon. The only thing that matters for those spin is the external field. So the sum of the sigma U, sigma V, XUV for U non-moving. So instead of doing a union bound over each of those sigmas individually, I can do a union bound over the value of this thing. Okay, so now do union bound over the value of, let's call this QV. Over the value of QV. Of course, QV is a continuous random variable. It can take value between -n and n. But in fact, to decide if this move is between 0 and epsilon, I just need to know this up to, I don't know, epsilon over 10. Okay, so I do a union bound over the value of the external field, but just up to epsilon over 10. So do union bound over the value of QV up to epsilon over 10. So I just discretize this interval minus n with a mesh of size epsilon over 10. So I have n over epsilon total values up to a constant. And I need to do this for each v which is moving. How many moving v's do I have? I have s moving vertices. So I just get n over epsilon to the s. That's the union bound. Okay. So now, the next thing. Okay, good. So let's see what happens now. So now, we would like this to be useful, right? So we want, that would be nice. So we want this to go, in particular, we would like this to go to 0. Okay? So we need this n over epsilon to the s, the number of distinct vertices, times, let's forget about phi now, epsilon to the rank of L to go to 0 as n goes to infinity. We need more than that because here I fixed the sequence of moves, but certainly we need at least this to be true. Okay, so good. So that means that we need the rank. You see, there is an epsilon, 1 over epsilon here, and we will want to take epsilon to be really small, like 1 over poly n. So we want the rank to beat this S. Okay? So we need the rank of L to be bigger than, let's say, 1.1 S of L. Okay? If this is true, then what we get, then the bound becomes n to the s times epsilon to the 0.1 s. So if I just take if I just take epsilon again to be 1 over n to the 100, I'm done. Okay, this is going to go to 0. So the problem is, this is still not enough. Even this is not enough. So first of all, we still understand, okay, it's already 4 p.m. and we still understand nothing about the rank, but more than that, there is another union bound over all the moving sequences. Okay, in fact, we need n to the L, so that's the union bound over the moving sequences, times n over epsilon to the s, times n times epsilon to the rank to go to 0. So what we need is also that the length of the sequence, if we have a bound like this, we also want that the length of the sequence we are looking at should be comparable to the number of distinct vertices that are moving. Okay, so we want L of the sequence that we're looking at to be of order of, or O, capital O, of S of L. Okay, so we don't want to have long sequences with only few moving vertices. That would be bad for us. And now, let me tell you the next lemma. So the next lemma is going to say that exactly in any sequence long enough, there always exists not a subsequence, a sub-block in that sequence where all of this is satisfied. So let me say it. So for any L with, let's say, the length of L, so this little L of L, I hope it was clear, I mean the length of the sequence, which is 2n, there exists a block, B, included in L. So that's a continuous sub-block of the sequence L, such that the length of this block is exactly twice the number of distinct vertices in that block, okay, which is one of the things that we wanted. And the rank of this block is at least 1.25, 1.1 would have been fine, times S of B, which is the other thing that we wanted. Okay? So this lemma now finally is true. So if you combine with what I just said here, it's really easy to check that now if you just take epsilon to be 1 over poly n, you will get that this tend to 0. So let me just conclude now with how you can think about this rank. Okay, how could you prove such a statement? Okay, so how to think about rank? So we are looking at the rank of those alphas. You remember, so we have V1 up to VL. This corresponds to alpha 1 up to alpha L. Alpha, let's say T of U VT, that was sigma U, let's say sigma T U, sigma T VT. And alpha T of UW, that was 0, okay, if VT is not in UW. Okay, you remember that was the definition of alpha T, okay? Now, okay, so that was the definition of alpha T. So the rank of these alphas, you see, the way I want to think about it is as a matrix, okay, where here I have the columns, I have L columns. The number of rows is E, okay, for each thing I have E. So if you see it column-wise, you see that I can forget about this sigma T of VT. That's just one scalar for the entire column. So if I care about the rank, I can just forget about this. You can also see that because I only care about the product of those things, it's enough to assume that I start from sigma naught, which is the all one vector. Okay, so assume sigma naught is the all one vector. This you can see it because row-wise, you can just multiply by the initial spin of U times the initial spin of V. And then everything is like if I was starting with all ones. Good. So now the only thing that I want to tell you is that the rank is at least S. Okay, that's the trivial lower bound. And the work, you know, if I had 10 more minutes, would be to show to you that you can get a bit more than 1 times S, 1.25 S. So let's see just this, just the rank of is at least S. So we have those moving vertices, and they move at times, let's say, T1 up to TL. Okay. So let's look at those times, T1 up to TL. Okay, so these are different columns. And let's fix W, which is non-moving. Some vertex that doesn't move. Let's assume that there is one. And we're going to look at the rows which are given by V1W up to VLW. What do I record in this matrix? I just record the spin of the corresponding vertex at that time if this is a moving edge and otherwise 0. So let's look at V1W. So V1W, at time T1, V1 is moving. So I record the spin of W. What is the spin of W at this time? It's 1, because I assume that I start with all ones. After that, at all these other times, V1 is not the guy moving. So I'm not recording anything. W is non-moving, so I record 0. Now for V2W, at time T1 is not moving, time T2 it's 1, and then 0. Okay, so this matrix is just the identity. Right? So the rank is the number of, I mean, it's just the size, which is S, sorry. Okay, there were repetition in the way this was written, sorry about that. So this is the trivial bound. And now if you work a bit more, you look at really what this matrix means, you can prove two things. You can prove the rank is always bigger than S plus S2 over 2. S2 is the number of vertices that repeat. So that's always true. And you can also show that there exists a block such that the rank of this block, the subblock, is at least S plus S1 over 2, where S1 is the number of vertices that move exactly once. So if you combine those two, you see that you get S1 plus S2 over 4, and S1 plus S2 is S. Okay, so you get S plus 0.25 S. I think I'm done. Okay, thanks.
Maybe time for 1 or 2 quick questions.
What if you want like a local peak that stands out, so you can't move like 2, 3 vertices over?
Okay. Yes, that's a good question. That seems more difficult. Yeah, I never thought about that question. Yeah, I don't know. Can I say anything smart? No, it's a good question. Yeah.
A lot of the proof was preoccupied with, what if we chose some really bad sequence of flips?
Yes.
So in terms of implementing this, I mean, is the rank useful in terms of guiding you to choose, which flips are going to help?
So I didn't try to do that. I tried to do actually really bad implementation, really trying, to slow down the process. Like take the one, which makes as little progress as possible, and still it converges really fast. So, yeah.
All right, join me in thanking Sébastien.